All right, so let's move on to chapter 7, where we will be talking about chemical bonding and molecular geometry. So, in chapter 7, we are taking the concepts we learned about in chapter 6, electronegativities and the trends on the periodic table, and how those trends of electronegativities manifest itself into chemical bonding descriptions. So, in this course, we've already talked about two different types of bonding: ionic bonding and covalent bonding. Ionic being a substance that is bonded through a transfer of electrons, typically a metal and a nonmetal, and then covalent bonding, where there's a sharing of electrons, and that's between two atoms or elements with similar electronegativities. We'll look into how we can draw some of these structures using Lewis dot symbols and Lewis structures, and we'll talk about how the differences in electronegativities of atoms results in polar molecules versus nonpolar molecules, and we'll also look at how these molecules look like in 3D space. So there are three types of bonding descriptions that chemists use. The first one here being metallic bonding. This is the bonding descriptions with elemental metals, so like platinum or gold, and we'll expand more on this later. But typically, with metallic bonding, these metal atoms are bonded to several other atoms in the structure, in a network structure, and those electrons are delocalized, meaning that they can move freely throughout the whole structure. So, this is a reason why metals are typically conductive, that they can conduct electricity and heat very well because of those delocalized electrons within their structure. The other two bonding descriptions that we've already talked about: ionic bonding versus covalent bonding. Ionic bonding is formed through electrostatic interactions between ions, electrostatic meaning charges. So we have positively charged cations attracted to negatively charged anions, and then they pack together into a network structure. And so those ions are formed through the transfer of valence electrons of those neutral elements that are, or atoms that are a part of that structure. So, for example, salt or sodium chloride, we know that sodium on the periodic table, that element is metallic, it is a metal, and chlorine being on the right side of the periodic table is a nonmetal. So, going back to our naming conventions of ionic compounds, we can identify sodium chloride as an ionic compound because it's composed of a metal and a nonmetal. So if we take that application of identifying the cation and anion, it's a metal and a nonmetal, we can apply our concepts of electronegativities. Metals tend to be have low electronegativities, so they tend to form cations, while nonmetals have high electronegativities and will form anions. So through that dichotomy, or that big difference in electronegativities, so sodium has a low electronegativity, chlorine has a high electronegativity. So what's going to happen is that an electron from sodium will be transferred to chlorine. So then we can form a sodium cation and a chloride anion to form an ionic bond. And so the big point here with ionic bonding is that in order for an ionic bond to occur, you need a large difference in electronegativities of the two atoms involved in bonding. And that is what pushes that electron transfer of valence electrons for those ions to form. So this contrasts to covalent bonding. So covalent bonding is when there is not a large difference between electronegativities of the atoms involved. So I'll say large delta En, or difference in electronegativity for ionic bonding, versus small difference in electronegativity for covalent bonding. So this involves a sharing of electrons because there's not a large electronegativity difference. There's not a driving force for electrons to move from one atom center to another. So instead of a complete electron transfer happening and forming ions, instead those two atoms involved in the covalent bond share their valence electrons. So an example here is a carbon-carbon bond, essentially the backbone of all of organic chemistry. So I know that the electronegativity differences between these two atoms are zero because both these carbon centers have the same electronegativities. So the difference between them will be zero because they're the same. And so, since there's no difference in electronegativity, there's no driving force for an electron transfer happen to occur. That one carbon center isn't going to want one of the electrons more than the other. So instead, what happens is you get a sharing of electrons between those two carbon centers. And so this is the basis of a covalent bond, but typically we draw, instead of the two electrons, next to each other, we draw a bond between those carbons. So this would be an example of a carbon-carbon single bond, where that bond is produced by two electrons being shared by those two carbon atoms. So all of these bonding descriptions, covalent and ionic bonding, involve electrons that are in atoms' valence shell. We kind of hinted at this in chapter 6, where we said those inner core electrons typically aren't involved in chemical reactions because they're deeper within the atom, they're harder to remove, and so that's why valence shell electrons are the electrons that we care about, and the reason why noble gas shorthand electron configurations are fine to write out when looking at reactivity of atoms. So let's look into another way that we can describe these valence electrons through Lewis dot symbols of atoms. So so how can we denote valence shell electrons in different atoms? So let's take an example, calcium. So the first step here is to write out the electron configuration for this atom. So let's do that for calcium. So let's take out our periodic tables and write out the electron configuration for calcium. So let's do the full electron configuration. So 1s2, 2s2, 2p6, so that brings us to neon. Now we're at sodium, so 3s2, 3p6. So now we're at argon, and then 2 more electrons to get to calcium, so that is 4s2. All right, and so again, let's identify the valence shell electrons. Valence shell electrons are the outermost, the electrons with the highest N value. So here are our valence electrons. And so that leaves all of the rest of these electrons are our inner shell. And so those inner shell electrons aren't involved in chemical reactions. So we can just, this is the reason why we can just write out the noble gas shorthand version. So if we did that for calcium, that would be argon 4s2. So now what we've really done is just identified the valence shell electrons. So for here, there are 2 valence shell electrons in calcium's 4s2 orbital. All right, and so we've already kind of hinted at this, is that the group number typically denotes how many valence shell electrons are in that atom. And so that means, calcium is a group 2A metal, so it has 2 valence shell electrons. Any group 1A metal will have 1 valence shell electrons. Group 5A will have 5 valence shell electrons. So group numbers give us a hint in the number of valence electrons present in that atom. All right, and so a different way to denote, instead of writing out, letters and numbers like this to denote valence shell electrons, we can also show pictorially how many electrons are around a calcium atom. And so to do that, we can use Lewis dot symbols. And so to do that for calcium, you write out the element symbol, and now we need to denote how many valence electrons are around that calcium atom. So since there are 4 s2, or sorry, there's 2 s orbital electrons, we will draw 2 dots to denote each of those 2 electrons around our calcium atom. So right there, those 2 dots are the 2 4s2 electrons that we see in those valence shell electrons. So, and note how I put those 2 electrons together, because they are shared in the same s orbital. So the way that we denote this Lewis dot symbol also reflects on the orbital diagram that we could write for calcium. So for calcium, you have your argon inner shell, but if we wrote out the orbital diagram for calcium, so our 4s orbital here, we would have a spin up and a spin down electron in the same orbital, and so that's why we put those 2 electrons together there. So let's consider some other examples here in drawing those Lewis dot symbols for these different elements. So let's consider lithium. Again, write out the noble gas shorthand electron configuration. So for lithium, it would be a helium 2s1. So there's only 1 valence electron. That makes sense because lithium is a 1A element. So the number of valence electrons here is 1. So to write out the Lewis dot symbol here, you would write lithium, the element, and now we just need to denote 1 valence electron. So we just put 1 dot right there. So what about neon? So let's do neon as well. So if we write out the whole electron configuration here for neon, it's 1s2, 2s2, 2p6. So let's think about number of valence electrons. It's the outermost number of valence electrons. So if we count all of the electrons that have the highest n value or principal quantum number, that would be right here, 2s2, 2p6. So these are all the n equals 2 electrons. So if you count up all those electrons as those superscripts, there are a total of 8 electrons in neon's outermost shell. So to write out the Lewis dot symbol for neon, you write the shorthand symbol for the element. Now we need to write out 8 electrons. So 1, 2, 3, 4, 5, 6, 7, 8. All right, so there are 8 electrons around neon. And so I can kind of do the same thing as I did before, how these Lewis dot symbols are just another way we can rewrite the orbital diagrams that we did in chapter 6. So for lithium, here's its 2s orbital. If we wrote out the orbital diagram, there would only be 1 electron there. So you see that there's 1 electron, and that's symbolized by the 1 electron in its valence shell. So we could do the same thing for neon as well. If we just drew out the orbital diagram for neon, I can just draw all of it, I guess. So 1s, 2s, and then 2p, and then fill up all of those electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 electrons for neon. So to draw the Lewis dot structure, we only draw the outermost valence electrons, and so here are the 8 electrons that I've denoted here. See how all in the orbital diagram, all of the electrons are paired in neon. And same thing, I've denoted the same thing in the Lewis dot structure, where all of the electrons are also paired. All right, so let's do another example. So phosphorus. Phosphorus is a 5a element, so we would expect that it would have 5 valence electrons. All right, 5 valence electrons. So how do we draw out this Lewis dot structure? Again, writing out the electron configuration is a good way to help us get started and understand how those electrons pair with one another. I mean, I know that for phosphorus, we will start with, phosphorus, our element. So how do we draw out those electrons? So let's write out the electron configuration for those 5 valence electrons for phosphorus using Aufbau's principle and how we spread out all of the electrons first before we start pairing them up in a subshell. So if there's 5 valence electrons that we need to place for phosphorus, we put 2 of them in that 3s orbital first, and then we have to draw the other 3. 1, 2, 3, spreading them out so they all have the same spin. We want to maximize the spin. That's what Aufbau's principle says before we start pairing up electrons. So you don't want to write it like this. That's not correct. All right. So using this electron configuration diagram, we need to reflect the electron pairing around our atom here in our Lewis dot structure. So to represent the Lewis dot structure, I will place those 2 electrons that were in our 3s orbital. So those are the 2 3s electrons. Now we want to place those 3p electrons equally around the phosphorus in the different quadrants around the atom. So I'm going to draw them like this, because these electrons that I just drew, these are all unpaired. So you want to make sure when you draw the Lewis dot structure is that the unpaired versus paired electrons are reflected in that. So this is the Lewis dot structure for phosphorus. Are we going to do other ones? Yes. Okay. So let's do some other ones. We won't, do every single step, but let's see if we can't do carbon and magnesium for our Lewis dot structure. So again, we want to write out the electron configuration. So for carbon, it is helium, 2s2, 2p2. And for magnesium, it is neon, 3s2. All right? And so, again, identify number of valence electrons. So for carbon, there's 4 valence electrons. For magnesium, there's 2. Makes sense because carbon is a 4a element, magnesium's a 2a element. And so to write out the Lewis dot structure for carbon, we want to draw those 2s electrons, and then there's 2p electrons that we want to space out. Again, so if you actually drew out the electron diagram, it would look like that. And then we can do the same thing for magnesium. And so there's 2 electrons in the 3s subshell, so we will just draw it like this, where those electrons are paired. And so you could draw the electron diagram like that as well. 2s, 2p. So again, the big point here is that you need to reflect your paired versus unpaired electrons within your Lewis dot structure. And so typically what I do is I reserve this space, the right-hand side, as my s orbital, and then these other 3 as my p orbital subshells. That's typically what I do. But you could do it in any arrangement as long as you're indicating the correct electron pairing. All right, so now that we understand Lewis structures, let's look into covalent bonding, or sharing of electrons, and bonding descriptions that involve sharing of electrons. So covalent bonds are formed between 2 nonmetals, and that's because the electronegativities of 2 nonmetals typically are similar. So we have small differences in electronegativities of those 2 atoms. So the electrons will be shared rather than transferred. So let's consider the simplest covalent molecule, diatomic hydrogen, H2 gas. So each hydrogen atom has 1 electron associated with it. Its electron configuration is just 1s1. So each hydrogen atom center has 1 electron. And since they have identical electronegativities, there's no driving force for an electron transfer to occur. So instead, these 2 hydrogen atom centers will share their electrons. So here is a diagram that we can show the internuclear distances between 2 hydrogen atoms when they form a covalent bond. So right here on this side of the graph are when the neutral hydrogen atoms are far away from each other. This x-axis is internuclear distance. So over here on this side of the graph, this is when the atoms are far away from each other. So what this graph is showing is the energy of the system, of the 2 hydrogen atom centers when they're at different distances away from each other. So what you see is, if we start here on the graph, or here, our 2 hydrogen atoms are far away from one another, and it has a certain energy associated with it. But then what happens is, as we start to bring the hydrogen centers close to one another, the energy dips down. And this dipping down is telling us that when we bring 2 hydrogen atom centers close to one another, that they can now start sharing electrons, and we can create a stable molecule. So right here on this graph, at the center here, is the minimum energy, or the lowest energy of the diatomic hydrogen atom at a certain distance. So those 2 hydrogen atoms at a certain distance away from each other. So at this distance is what we expect a hydrogen-hydrogen bond length to be, because at that distance, the sharing of electrons has become optimized within that certain molecule. And so what we see as we go up, as we bring those 2 atom centers even closer to one another, what actually starts happening is that the 2 positively charged nuclei become somewhat close to one another, and now there's a repelling action happening. And so that's why this graph, the energy goes way up, because now as you bring those 2 atoms close to one another, they're like rubbing in against each other, and now that molecule is no longer stable. So at this low point of the energy, you're actually maximizing the attractive forces between protons and or your positively charged nucleus and electrons, while minimizing any repulsions between electrons and electrons and protons and protons. So that's what this slide is showing, is that this minimum energy that you see, the typical bond length that you would expect in a hydrogen atom, is when you have balanced the attractive forces between protons and electrons between your 2 hydrogen centers, while minimizing repulsive forces between the 2 hydrogen nuclei centers, because you don't want them to be too close to one another, or it'll start to repel one another because they're both positively charged, and reducing or minimizing repulsive forces between 2 electrons involved in this chemical bond. So this is what this graph represents, are the balancing act between repulsive forces and attractive forces between the protons, the 2 nuclei, the 2 positively charged nuclei, and the 2 electrons involved in a hydrogen-hydrogen molecule. And so what happens is, when we bring 2 hydrogen centers close to one another and we achieve that ideal bond length, now those 2 electrons can be shared with one another, and we've now balance the attractive and repulsive forces between those two atom centers. So that is the basis of all covalent bonding, where electrons are shared. So you see here how we bring these two atom centers close to one another and we can share those electrons. So we don't typically draw covalent bonds in this way where we draw each individual electron. We typically show them as a line between them, a dash. So that dash actually represents two electrons being shared, or an electron pair being shared to form a covalent bond.